Have you ever wondered why ChatGPT types its answer instead of just showing it all at once? Believe it or not, it's not a stylistic choice to make it look human. It's a clever hack to hide one of the biggest engineering hurdles in AI: latency. In the world of large language models, speed isn't just about your internet connection. It's a brutal, high-stakes tug of war between math, memory, and the speed of light. Let's break down why LLMs are slow and how we're fixing it. When you hit enter on a prompt, the model enters the pre-fill phase. Think of this as the model reading your entire prompt in one giant gulp. It's calculating the relationships between every single word you sent. This is compute bound. This gives us our first major metric, TTFT, time to first token. If your TTFT is high, you're just staring at a spinning loader. For a great user experience, we want this under 200 milliseconds. Once the model starts talking, it enters the decode phase. Here's the kicker. LLMs are autoregressive. That's a fancy way of saying they can't predict word number 10 until they've finished word number 9. To generate that next word, the model has to move billions of parameters from the GPU's memory into its processors. This gives us our second metric, TPOT, time per output token. That's the streaming speed you see on your screen. So, how do we make it faster? We can't change the laws of physics, so we cheat. First, streaming. Instead of waiting for a 500-word essay to finish, we send each token to the user the millisecond it's generated. It hides the latency by giving you something to read immediately. Second, KV caching. Without a cache, if the model is generating the 50th word, it has to recalculate the math for words 1 through 49. That is, big O of n squared complexity. It gets exponentially slower as the chat gets longer. The key value cache stores the internal mathematical representations of all previous tokens in the GPU's VRAM. The result? When word 50 is generated, the model only calculates the math for that one new word. It turns an exponential problem into a linear one. Then there's speculative decoding. Imagine two models working together. You have a target model, the big, smart, slow one, and a draft model, a tiny, lightning-fast one. The tiny model quickly guesses the next 10 tokens. It's 10 times faster, but often wrong. Then, the big model looks at all 10 guesses in one single parallel pass. If the big model agrees with the first 4 tokens but hates the 5th, it keeps the 4, corrects the 5th, and throws away the rest. You get the brilliance of the giant model at a fraction of the time. Finally, quantization. If KV caching saves time, quantization saves space. Most AI models are born heavy, using 16-bit floating point numbers. It's like trying to describe a color using 65,000 different shades. Precise, but a nightmare to move around. When we quantize to 4-bit, we're saying, you don't need 65,000 shades. 16 colors are enough. By shrinking the data, we reduce the memory footprint by 4 times. This is how you run a massive 70 billion parameter model on a consumer GPU instead of a $20,000 server. At the end of the day, latency is a UX problem disguised as a hardware problem. By measuring your TTFT and TPOT and using tricks like quantization and streaming, you can turn a laggy AI into a seamless collaborator. Don't forget to like and subscribe for more deep dives into the AI stack. I'll see you in the next one.